Okay, so we're all hearing about AI models constantly, right? They're everywhere. But have you ever stopped to think about what's actually making them run? It's not just the model itself. In this explainer, we're going to pull back the curtain and look at the whole shebang, the entire machine learning system.
You've probably played around with AI that can write a poem or create some wild image. It feels like magic. But how does that magic get from a researcher's computer into an app on your phone? What does it really take to run one of these things in the real world? Well, I'll tell you, it's a whole lot more than just the algorithm.
Right. So here's a great way to wrap your head around this. Think of the machine learning model as the brain. It's the super smart part, the part that does all of the thinking. But you know, a brain floating in a jar can't really do anything, can it? It needs a body. That's what the machine learning system is. It's the entire body, the skeleton, the nervous system, everything that allows that brain to actually do something useful and connect with the world.
So, if we're gonna understand this body, we need to look at the blueprint, right? Let's dive in and start with the absolute fundamentals, laying the foundation for what makes up a complete ML system.
Okay, so the key word here is integrated. An ML system is an integrated system. And what that means is, it's not just the model. It's all the other stuff, the plumbing, really, that you need for processing data, for serving up predictions, and for keeping the whole thing running. It's the complete package that actually makes AI useful. And you have to understand, building one of these systems isn't like building a bridge where you finish and walk away. Nope. It's a life cycle. It's a continuous process. You start by figuring out the problem, you get your data, you build the model, but you're not done when you deploy it. In fact, that's kind of just the beginning. The really hard work is the maintenance, that constant loop of watching it, updating it, and making it better over time. And make no mistake, these systems are everywhere already. They're out there changing our world as we speak. We're talking about projects like FarmBeats, which is literally helping farmers grow more food. And on the other end of the spectrum, you have the mind-bogglingly complex systems that allow self-driving cars to see and navigate our streets. This stuff is real, and it's here. Okay, so we've got the basic blueprint down. But here's the thing. Just getting a system to work isn't enough. It also has to be efficient. And that brings us to the next huge piece of this puzzle, performance.
You know, for the longest time, the approach in AI was pretty simple. Just go bigger. Bigger models, more data, more compute power, throw everything at it. But we're starting to hit a wall with that. This bigger is better approach is running into a classic case of diminishing returns. The costs are skyrocketing, but the improvements we're getting are getting smaller and smaller.
And this is where something called AI scaling laws becomes super important. Basically, these are rules of thumb that help us understand the relationship between a model's size, the data you feed it, and how well it performs. And what they show us is that just throwing more compute power at something isn't a magic fix. It's not a silver bullet. You can't just keep feeding the beast and expect amazing results. You have to get smarter.
So what does getting smarter mean? Well, it boils down to tackling efficiency from 3 different angles. First, you can make the algorithm itself more clever, so it just needs less brute force. Second, you can improve the compute, the actual hardware it runs on. And third, you can focus on data efficiency, figuring out how to get the same or even better results with less data. It's like a 3-pronged attack on this performance problem.
All right, so we've got the blueprint. We know it needs to be efficient, but now let's talk about where the rubber really meets the road. Let's talk about the real world, that messy, chaotic, unpredictable place where these systems actually have to survive. This is AI in the wild.
And there's actually a whole field dedicated to taming this chaos. It's called ML Ops, which stands for Machine Learning Operations. And it's basically this cool blend of 3 different worlds: machine learning, DevOps, which is all about running software, and data engineering. You can think of it as the official playbook for how you run AI in the real world without everything falling apart.
One of the absolute biggest things MLOps has to deal with is a concept I love called hidden technical debt. This is all the sneaky, long-term problems that you don't see when you first build a system. It's the stuff that quietly piles up in the background and then, comes back to bite you months or even years down the line.
And this debt takes some really wild forms. I mean, they sound like something out of a sci-fi movie. You've got things like correction cascades. That's when you fix one tiny bug, and it causes a chain reaction that breaks 10 other things. Or undeclared consumers, where another team starts using your model's predictions without telling you, and suddenly you can never change it without breaking their stuff. I mean, this is the real nitty-gritty challenge of keeping these systems alive.
And that leads us to the final, and honestly, probably the most important layer of this whole blueprint. We know how to build these systems. We're getting better at making them efficient and running them in the wild. But the big question we have to ask is, are we building them responsibly?
This means thinking about things like fairness, transparency, privacy, and safety not as, optional add-ons you tack on at the end. No way. These have to be core design principles right from the very beginning. The thinking is, if you want people to trust these systems and for them to be truly reliable, they have to be understandable, secure, and work fairly for everyone. They have to be baked in from day one.
And this idea of responsibility goes even beyond the code itself. We also have to talk about a pretty uncomfortable topic, the environmental cost. Training these massive AI models takes an absolutely insane amount of electricity. So that begs the question, what's the real carbon footprint of AI?
Get ready for this number. Just let it sink in. 626,000 pounds of CO2. And that's not for the whole industry, that's for training one single large AI model. To put that in perspective, that is nearly 5 times the entire lifetime emissions of an average car, fuel and all. It's a staggering number, and it really forces us to ask what the true cost of all this progress is.
So as you can see, a machine learning system is so much more than just a cool algorithm. It's a complex, almost living thing that has this massive, sprawling impact, from the technical weeds of hidden debt all the way up to its global carbon footprint. And as these systems become more and more woven into the fabric of our world, the ultimate question we're all left with is, how do we make sure we're building them for the good of everyone? Thanks for joining me on this.